Today's presentation topic is on high performance compute clusters. HPC is the term that we use for interchangeably with high performance compute. A little about myself here. My name is Jim Pond. I'm a licensed engineer. I have been for pretty much 30 years. Electrical engineering grad from Queens. My specialty is all things compute. I've been in enterprise IT, data center type server technologies for pretty much my entire career since the 80s. Right now, I work for Dell Technologies. I'm the Canadian lead for all things related to high performance computing and server solutions. The marketplace is primarily in the higher ed, as well as some in the federal government. There are smatterings of these technologies around, but those are the largest consumers in Canada. So what is a high performance workload? So class of applications that I listed off here on the slide. We have kind of in order the more traditional high performance computing workloads: computational fluid dynamics, finite element analysis, electronics design automation. Those are the classic types of applications that we run on high performance compute clusters. Okay, computational chemistry is another large one. These are kind of characterized by floating point requirements. Okay, so these are applications that take advantage of the floating point capabilities of the processor. Over time, like we're kind of in a funny transition, and we have been perhaps for the last 4 or 5 years, where these types of solutions have been used to run newer types of workloads. And I've listed some of them here: big data analytics, machine learning, and all things AI, CGI rendering, render farms, that type of thing. Very popular in media entertainment space, real-time image analysis, fraud detection, things like this. Okay, so these are newer classes of applications which have been shoehorned onto a traditional HPC compute infrastructure. Okay, so that in a nutshell, right there, that's the type of software it is that folks have, and we're going to talk about sort of the infrastructure that you would deploy to run these types of applications in a large scale fashion. So there's a few different sort of models or constructs to be aware of. The first is this idea of embarrassingly parallel. Okay, and then an embarrassingly parallel workload is one where there is no dependency between parallel tasks. Okay, so you have lots of parallel tasks going on at the same time, and they don't exchange information amongst themselves. Okay, the problem itself can be broken into a number of parallel tasks in an easy fashion. So examples there, the really good example would be genomics. Okay, so that's the most popular embarrassingly parallel job that's out there. So the opposite of embarrassingly parallel, there's no catchy phrase like embarrassingly parallel to refer to the opposite, but those are non-parallelizable or sequential type applications. And in those cases, you do have parallel tasks, but and so you're running them on a large scale machine that has the ability to run multiple tasks simultaneously. However, you need to be able to have those tasks or threads of execution talk to one another and exchange information, exchange messages between them during execution. Okay, the problem is inherently serial in nature, not necessarily parallel, and so you're kind of using the magic of software to break up your job into a parallel job. So if you want to do computation of irrational numbers, these sorts of things, the non-parallelizable type of job is very typical for the applications that I listed on the previous slide. So an example there to sort of illustrate the point would be if you consider 100 people in an auditorium, each with an IKEA bookshelf in a cardboard box. And if you have those 100 people, each with their own bookshelf, and you tell them all to start at the same time, and then at the end of the process, you have 100 completed bookshelves. Okay, that is an embarrassingly parallel workload. The alternative of that is if you have the same 100 people in the auditorium, but they're all working on one IKEA bookshelf. Okay, so those 100 people are cooperating, with the little hex key, to put together that one bookshelf. That is a non-parallelizable or a sequential job. All right. So those are the two different constructs. Now, the significance of this is that these two different types of jobs require different types of hardware. Okay, and different infrastructure. And so the second type of job is really what I'm going to focus the discussion on here today. And it's really more akin to when we talk about high performance clustering. That second type of job is really what those things are built to do. Okay, it requires a high speed interconnect in between your compute nodes. It requires a shared high performance file system, and it requires quite a bit of software to coordinate the operation of multiple compute nodes. Okay. The embarrassingly parallel workloads don't require any of that stuff. Okay, so the infrastructure that you would deploy to run an embarrassingly parallel workload, like a genomics application, is much simpler. Okay, so how do we get to a cluster? Okay, because there's a bunch of folks who run this class of application, but they don't have a cluster. So typically these workloads start off with an engineer or a scientist or some other type of user running the software on their laptop, their personal machine. And depending upon what it is that they're actually doing and how frequently they do it and how big their data sets are, that's perhaps a perfectly acceptable solution. Now, sometimes what happens is when those models get large or when the business task gets super critical, that everyday laptop is not good enough to run the workload. And so that user goes out and gets himself a better machine, typically what we call in the computer business, a workstation class machine. And they run that on their desktop and they're happy running their workload because it's an improvement over their laptop. However, if that thing runs out of gas, where do you go from there? Okay, so then what you do is you take your application and you break it up into components so that a portion would run on your desktop and a portion would get batched out to a server. Perhaps when you're starting this journey, you're given a portion of a local server to use, or maybe you use an instance in the public cloud. Some form of server resource is made available to you to dispatch the batch portions of your job. When that gets too egregious, where do you go from there? Well, what you do is you perhaps get your own server if you're a user, or perhaps you get a group of servers. Okay, and so that group of servers we refer to as a cluster. And so this is how these things tend to develop. We get a lot of people who tinker with the technology, tire kickers, and then they start to put it into production or the business that they're involved with. It becomes an important critical element. And therefore, then the business starts to invest in their infrastructure, and then that's when they get into a cluster. Also, in this journey, sometimes what happens is maybe a portion of the workload can be spun off to GPUs, what we call accelerated compute nodes. And so sometimes in the infrastructure, you'll have one or more GPU-enabled machines to run a portion of the jobs. Some portion of these workloads lend themselves to running on GPUs, and some do not. I'll talk about that further in the presentation. So, a high-performance cluster. What are the components that we talk about here? Well, servers, the computers. We call those compute nodes. They run the applications. Also, servers are used for performing administrative tasks. Some servers are deployed as what we call accelerator nodes. Again, those are the machines that have GPUs in them. So there's a sort of a mix of different types of servers that you would deploy inside a cluster. Then there's a network. The network that's used to interconnect your servers is typically referred to as a fabric. That's a high-speed dedicated interconnect. That would be separate from your management network. You typically deploy an Ethernet network for your out-of-band management. And then you have some connectivity to your production network. That typically happens at the head nodes, not necessarily your compute nodes. The head nodes would be dedicated to connection to your production network. Then in terms of software, you'll have a few different pieces of software, key pieces of software here. One is for batch scheduling. So on your head nodes, you would typically run a batch scheduler, for example, Slurm, very popular choice there, and that manages all your batch processes because all these compute nodes, the applications they're running are all in batch, and so that batch scheduler coordinates the scheduling of execution across the nodes in the cluster. Another software application that you would have would be for cluster administration. So that would talk to your scheduler that allows you to get a view of your resources that are available in the cluster, how busy things are, if everything's working, et cetera, so forth. And then not uncommon to use the vendor's stack for some manner of administration, for instance, patch management, that sort of stuff. And then finally, the compute node stack, the software that actually runs on your nodes. And typically you deploy the compute nodes with an identical configuration, identical hardware, identical software, identical patch level. And so you'll typically use your administrative tools running on your head nodes to dispatch images to your compute nodes. And that stack that runs on those compute nodes would be like the operating system. It would also include MPI libraries. MPI is a message passing interface. That's the library that exists on across the cluster that would manage the cooperation between the nodes. And so when you go and deploy your software, finite element analysis, et cetera, so forth, those things would be MPI enabled. And those would allow the use of their software across multiple nodes. So the MPI stack would be loaded on each of the compute nodes. And then finally, storage. You would deploy a high-speed parallel file system. It has to be parallel so that it can be shared simultaneously between all your compute nodes. There's no file locking here. It's all shared. And that's typically fabric attached. You could also use a traditional network file system, either KIFS or NFS, typically NFS, because these are all usually Linux-based. And that's where your home directories would be. So kind of what happens in practice is your traditional file system is relatively cheap storage, and that's where you kind of stage your data. And the high performance parallel file system is expensive storage, and that's mostly used for caching or for staging your data. You would load your data from your file share onto your file system, run your jobs, get your results, and then sort of push it back onto the file share. That's typically the way you do it because it's expensive to use that parallel file system. Also, you don't typically back that up either. Okay, so if you want to do backups, you would do it on your of your file system of your network file system. And then also there's local storage on your compute nodes. Besides your OS stack, perhaps you put temporary files there as well. So that's also available to you as storage. So that in a nutshell, those are the components it is of a cluster. Okay. So moving on. So historically, okay, because people have been running scientific and floating point jobs for decades and decades and decades. Okay. And so traditionally, when people started running these things, kind of in the 60s, the way they would skin that cat would be they would deploy large single compute nodes. Okay, and so this is where the industry started. Cray was really the market mover at the beginning of the era. There were other players that came in. Convex is one of them, and then there was a bunch that appeared in the 90s. Okay. In this world and in my world, the compute world, you hear these terms scale out versus scale up. Okay. And so a large big box is what we call a scale up architecture, right? So you buy yourself a big refrigerator of a computer, and if it runs out of steam, you put more electronics into it. You add processors and memory into that big box. That's a scale up architecture. Modern clusters are built in a scale out architecture, right? And so you add more smaller commodity x86 based servers if you want to increase the scale of your cluster. That's the modern approach, a modern HPC cluster. Large monolithic compute nodes are still sometimes used. So you will see nodes in a cluster that are 8-way, for example, if some jobs just cannot be parallelized at all. perhaps older code. It is not happy running across multiple machines, or they're not MPI enabled. Sometimes you'll still see them, kind of rarely. If you consider an accelerator node, which is what I referred to earlier as a server with GPUs in it, that's kind of a large monolithic compute node, and those are very popular in a modern cluster, accelerator nodes, especially as more and more code gets ported to use GPUs. Now, like I said, I'll talk about that in a second. When customers go and build these things, they have a choice between buying white box, what we call clones, or tier one manufacturers from people like Dell, HP, Lenovo, etc. So those two choices are available to customers. In terms of roles, and I think I mentioned this, there you have compute nodes for actually running the software. You have head nodes for administrative functions, and people call these things different things. They call them login nodes, the administrative nodes, head nodes. But basically, these are for administrative functions. Okay, and then also you may find in the cluster storage nodes, which would be where you would have, if you don't have a parallel file system, this is where you'd have NFS type mounted storage. Okay, all right. Moving forward, Fabric Interconnect. All right. So typically, 99% of the time, in a high performance cluster, Infiniband is used as the Fabric Interconnect. State of the art there, and Infiniband is a technology that's owned by Mellanox, and Mellanox is a company that's owned by NVIDIA. That state of the art Infiniband is called HDR. That's a 200 gigabit fabric. Very, very, very low latency. That's why people use it. Consider the speed of Infiniband at less than a microsecond of latency versus regular old Ethernet at 12. Okay, so it's 25 times slower. There is a version of Ethernet called Rocky, RDMA over converged Ethernet, which is an alternative to Infiniband. Not quite as good as Infiniband, and not really very well deployed either, but it is an option. And there's some serious work around trying to use Rocky, because the economics of using Rocky is much more motivating than the economics of Infiniband, which is a relatively expensive technology. You can basically, when you build out a network, an Infiniband network, you assemble it using multiple switches, multiple smallish switches. The current HDR switch is a 40-port switch. Okay, that's basically it. They don't build a lot of different switches. That's the one that they build. They build a large director class switch, but that's not very typically deployed. So it's mostly that 40-port switch. So if you have anything more than 40 nodes, you need more than one switch. And so you buy multiple switches and you tie them together in various different topologies, the most popular of which is fat tree. Okay. And these are non-blocking topologies, which allows line speed node to node. The cabling, okay, of an InfiniBand network is expensive, not just the switches and the switch ports, but the cabling to tie it together is expensive as well. And so there's a little bit of a science to lay out your racks and where do you put the equipment in the racks to try to minimize the cable runs. Okay. To put it in perspective, I put a little chart here, the USD list price, give you an idea of some of the pricing. You get a 2-meter cable. It's $200 US list, right? So, if you're talking 128 node cluster, that price adds up pretty quick. And if you're talking about longer cable lengths, you can see, like, once you breast 2 meters and get up into 3 meters, which you'll need at least 3 meters if you're doing connections between racks, it's over $1,000, right? So it's not an insignificant part of the capital cost. The other little diagram here I created was to put this into perspective. If you have a cluster with 40 nodes or less, and you have a 40-port switch, you're golden because you only need one switch. Okay, but let's say you needed 41 ports. Right? What if you've exceeded the capacity of a single 40-port switch? Well, and you want to still maintain non-blocking architecture. You still want a line-to-line speed between all the nodes in the cluster. Well, then you have to lay out a fat tree topology. And the little diagram here shows you that you need actually 5 switches, okay, if you go from 40 ports to 41 ports. So it gets real expensive to expand a cluster, okay, when you're talking Infiniband. So that's one of the features, the people in my business that you're dealing with quite a bit, is that how do I lay out my fabric? In terms of software, I think I went over this earlier, but just to lay it out there, on the compute nodes, you have the operating system. It's typically Linux. We typically see, like for the clusters that I'm involved in, where we use tier 1 servers, because obviously I work for a tier 1 manufacturer. The version of Linux that you would use would typically be one where the manufacturer has a great deal of support for. So CentOS is a very, very popular Linux distribution. People typically will not use a commercial version of Linux in these environments because it adds unnecessary cost. CentOS is very popular, and Ubuntu is probably number 2. As I mentioned, you'd load it up with MPI libraries so that your nodes can communicate. And then there's application software. And your head nodes, that's where you would run your scheduler and your administrative software. The storage side. So there's kind of 3 ways to provide storage to a cluster. You can get a high-speed, specialized parallel file system, and there's a few vendors out there. DDN is one of them. I have them at the bottom here. BGFS is another, a GPFS. These are different options for specialized parallel file systems. Okay, these attach directly to the fabric, and they're shared amongst the compute nodes. Another way to skin the cat is to use just regular NFS. Okay, so have a storage server that's fabric attached, and that would become your alternative to the parallel file system, much cheaper. Okay, so if you have modest requirements, perhaps that's the way you go. The third way to skin the cat would be use the NFS file system, use the storage server, but just attach it to the network. Okay, so that's the other way to do it. However, there's a ton of latency, as you move down that list. So people tend to use the parallel file systems on the fabric. And then, as I mentioned a little bit earlier, you will also have home directory storage, which is typically separate from the production storage. That's where you put your user data. You'll find in practice what happens is users get lazy and they'll leave their data out on that parallel file system because it's kind of a pain to keep moving it back and forth. There is some time required, especially with large data sets, to move it from one place to the other. So if they're lazy, they'll keep it on the production storage. The administrators of that storage probably not too keen with their users when they do that. And so they're encouraged to use that other tier of storage to store their files. If, as I mentioned, you may just have a storage server instead of a parallel file system, much, much cheaper. And there you go. I think I've covered it there. Okay. So one of the things that's impacting our industry is every time the vendors bring out new technology, it tends to consume more and more power. Okay, and so that is relevant really in 2 perspectives, the CPU and the GPU. So here on the left, I've given you a picture of some of the modern components that are out there. We have the latest Intel, what are called Cascade Lake. Actually, these are 6348s. So that would be Ice Lake processors from Intel, as well as the latest generation of AMD Milan processors. And then 3 different GPUs that are available to NVIDIA, 1 AMD. And as you can see, these draw quite a bit of stuff, quite a bit of power, sorry. And when you're talking about 2 processors in each server and maybe 64 or 128 servers, these numbers add up. So what I've done in the right-hand chart here is just I've built some sample configurations. So the PowerEdge R440, that's a 1U 2-socket machine. So I've outfitted it here just as a sample. Power for each one of those is 498 watts. If you're to jam an entire rack full of them, that's going to draw around 2,100 or 21,000 watts, 21 kilowatts. And I'll tell you, even though that's the first thing on my list here, many data centers can't even support 21 kilowatts in a rack. They can't bring that much power into the rack, and they can't cool that much heat out of a single tile. So even that is a challenge for many, many data centers. So I go down the list and I've got more exotic machines. Okay. And so if I look at a 4140 is a machine that has two CPUs, but it has 4 GPUs in it. Okay. And so each one of those draws about 1900 watts. And in a rack, if you filled up a whole rack, it would be 80,000 watts. Okay. A lot of power. And so you go down the list, we have a 6525. That's what we call a modular machine. So that's a 2U rack mount chassis that holds 4 separate 2-socket servers. So this is a density optimized platform. You can put 20 of those into a 4, or 21 of them into a 42U rack. That would be 84 servers, 168 processors. Okay, so if you fill up one of those with AMD processors, you're looking at up to 65 kilowatts in a rack. Okay, so and then at the bottom there, just for illustration, NVIDIA builds a machine that's a purpose-built GPU machine. That's a 6U machine. It's a 2-socket server, but it takes 8 GPUs. So 6,500 watts for each one of those in a fully populated rack, because there's 6 U's. Right, you get 7 of them. There's 45,000 watts. Right. So the point here is this stuff is great, and we love it, and it does a lot of work, but it consumes vast quantities of power, and it frequently exceeds the capacities of a typical data center. So this is a challenge that someone in my role I deal with all the time, every day. So the diagram on the left shows a typical data center where it has hot aisles and cold aisles. Air is drawn from the rear of a rack, computer rack full of computer gear, to the front. And so the cool air, in theory, goes in the back, and the hot air comes at the front. And then that hot air would be sucked up into the plenum, and it would go through HVAC, and it would get cooled, and the cool air would get discharged into the floor. Very traditional, been like that since, I don't know, 60s, maybe 50s. The problem with this is, if you look on the right-hand side, the hot air, which comes out of that front, tends to get sucked into the back, okay? And so you get this feedback loop where you're not getting a tremendous amount of efficiency. So air cooling, which is the traditional way to cool all of our equipment, is not really that great anymore for cooling the most modern equipment. I showed you that chart on the previous slide. We can easily get 80,000 watts on a tile. That represents just a tremendous amount of airflow out of a tile. And in fact, it's almost a physical impossibility to get that much exhaust out of a single tile. So there are some very creative solutions to this problem. And as we in time, the creativity will increase, certainly. To put this into perspective, I showed you some of the components that are currently available. Okay, so the currently available GPU, for example, state of the art, is a 400-watt device. Okay, so on the horizon, there are 1,000-watt GPUs. Okay, which is a tremendous amount of heat in a single chip. Realistically, anything above a 500-watt part is going to have to be liquid cooled. There's just you're running up against the bounds of physics at that point. And really, any CPU, because they're smaller, anything above 300 watts as we move forward is going to require some amount of liquid cooling. Okay, so air cooling will continue to be, of course, available and an option, but it will be increasingly relegated to supporting the lower performance computing solutions. Okay, so just to give you an idea of like some of the different options available to you, there's in-row cooling, okay, which has been around for a long time, and that basically puts air conditioning in the row with the equipment. There are chilled doors. And so chilled doors replace the regular door on your rack. And it, however, requires you to have some method of liquid cooling available to you in your room. Okay, so a chiller plant on the roof of some sort, or access to facilities water that you could perhaps circulate through the chill door. But you can do that without really impacting your infrastructure too much in terms of what's in the rack. Okay, you're just changing the doors. Sort of moving beyond that is a technology that we refer to as direct liquid cooling. And so in direct liquid cooling, there's actually plumbing that goes through the server itself. And on the back of the server, and you can see it in the upper right-hand corner of my slide, there's two pipes into the server. One goes in, one comes out. And then those pipes go to manifolds that run vertically in the rack. And so there's a manifold for water coming in. It's not water, it's liquid. And a manifold for the liquid going out. Okay. And those manifolds are shared by the servers in the rack. And then those manifolds are piped to a heat exchanger. And you can see they refer to that as a CDU, cooling distribution unit. That's a heat exchanger, which sits typically in the bottom of the rack. Okay. And so there's a closed loop within the rack. And then there's another loop that would go to your facilities. You can also have an end of row CDU. So like if you have a row of equipment, you've got a larger heat exchanger at the end of the row, and you would have a loop in the row, and then a separate loop that would connect that end of row CDU to your facilities water. So that direct liquid cooling, there's a lot of action there that is being analyzed and evaluated by high compute customers. And so then immersion cooling, that's something a little bit more exotic, but it's gaining more and more interest over time. And I know our company, amongst others, is investing in immersion cooling. And basically what this is a big freezer chest full of liquid, and you take the server and you immerse it directly into the coolant, right into that tank. So and when you do that, you have to remove the fans. Okay, so you can't have hard drives, because they're mechanical. You have to remove the fans. And so once all that stuff gets taken out, and as you can imagine, you just don't take your regular old server and you dunk it in there. You have to have help to make sure that your server is ready for this. You put it into that tank. The advantage of the immersion cooling is you can run that type of tank in ambient air. You don't need to cool the air anymore because you're cooling the tank. There is a very good reference available for immersion cooling. The customer is in a Middle Eastern country, and they have a number of these tanks in a room, which is really a glorified tent. So that's kind of proof positive that technology works really well for very, very dense computing solutions. Okay, you can see it right here. It can support up to 100,000 kilowatts. Okay, so that's a heck of a lot of heat being absorbed there. Just to change gears here, talk a little bit about GPUs. Okay, so GPUs are something which is of interest to a lot of computer users. We refer to that as accelerated computing. So when you hear this term accelerated computing, all it means is servers with GPUs in it. There's a lot of software work being done, primarily being promoted by NVIDIA, who really dominate the GPU market, to modify traditional HPC codes to take advantage of GPU architecture. It's obviously to their benefit that people implement compute nodes that have GPUs in them to run your code, and then they will talk about the price performance advantages of that type of infrastructure because you need less hardware potentially, albeit maybe more expensive hardware. The latest survey that I've seen is that 70% of the most popular HPC applications can take advantage of GPUs to some extent. Okay, so this is an important point: is that there's a difference between running all of your code on the GPU and running a portion of the code on the GPU. If you were to listen to NVIDIA, they perhaps would sort of infer that all the workload runs on the GPU, but the reality is pretty good extent of it runs on the CPU as well. And so it's important to have a balanced system to be running some of these codes, because it's not always easy to predict where it's going to be running. In a typical cluster, the customers, they typically run a great number of different applications on their clusters, right? They try to take advantage of that expensive resource by running as much as possible on there. And so it's not unusual to see 1,000 different applications running on a cluster. And so, all of those applications together have different profiles, some of which may take advantage of GPUs and some of which might not take advantage of GPUs at all. And so what you end up with would be sort of in a cluster, some nodes that are dedicated to GPUs, accelerator nodes, and then some nodes which don't. GPUs are great. If a good portion of the code will run on the GPU, then it's great. It's a great solution. They have literally thousands of cores in a GPU. If you can take advantage of them, your code will go lickety split. But GPUs are expensive and they do consume gobs of power. So there is a bit of a formula that needs to be determined whether it's great value or not. Okay. Now, I'm frequently asked about cloud computing. Okay, and cloud computing is it's a sort of a loaded term. In my world, we refer to the public cloud, which would be your AWS and your Azures. We refer to those as public cloud computing vendors, because in general, you can run a cloud without a public cloud supplier. Okay, really, the cloud is just a method of operation. You can run your own cloud and not use Azure. Okay, but nonetheless, there's considerable interest amongst HPC users to see if they could run their workloads on the cloud. If you listen to the public cloud providers, you don't need any equipment on-prem ever. The public cloud is the only infrastructure that you'd ever need. Some workloads are well suited to running in the public cloud, no doubt about it. However, others are not. For latency sensitive applications, like kind of what I've been talking about here today, the public cloud is usually poor choice because public cloud has built-in latency associated with it. We use this term hybrid cloud to refer to a solution where a portion of your equipment is on-prem and you're using a public cloud for a portion of your requirements. So you use the two together, and that's what we refer to as a hybrid cloud. In general, that combination gives you better value than going with 100% public cloud solution. So some of the aspects of the public cloud are very expensive. Data movement, for example, can be quite expensive. And so if you're moving a lot of data around, like if you have large data sets and you need to move it around, that can add up if you're using the public cloud for that. But if you are using the public cloud for short bursts of compute and you're not moving a lot of data, that can be a very attractive resource, okay, as an adjunct to your cluster. And in fact, some of the cluster management tools, for example, Bright Computing, allows you to manage a cluster that encompasses both on-prem resources and cloud-based resources. The public cloud providers, your Azures and your AWSs in the world, they offer a variety of different options to HPC users, including full GPU instances. Another example would be quantum computers. Okay, you can get instances of quantum processing power in the public cloud. So those folks in that business, they make a special effort to try to cater to as much of the requirements of HPC users as possible. As I mentioned, the concept of the cloud or hybrid cloud, you can extend the benefits of that model to on-prem. Okay, so people perceive the benefits of cloud computing as, look, I only pay for it on an operational basis. There's nothing to capitalize and like that. I can use it on demand, resource as a service, infrastructure as a service. I like that model. So that you can take advantage of those aspects of the cloud computing model, and you can extend that to your on-prem computing capacity as well. if you so choose. And there's software that allows you to implement such a solution, right? So there's a whole wealth of options that are out there. The final topic here is just to talk a wee bit about acquisition. Okay, so how do I see people buying these things? They're typically purchased as a single unit instead of being assembled over time. Unlike kind of how you would assemble your data center, where you would kind of, add a server or two. If you run out of gas, you add another one. You kind of, there's this sort of organic ebb and flow as you add and remove gear in a data center. Well, clusters really aren't built like that. They're built typically as a single unit. And you don't really expand them over time, okay? And kind of the reason for that is, and I say it here farther down the slide, it's kind of because of Infiniband, which is a total bear to do upgrades, okay? And so, what happens is there will be a point in time procurement exercise to purchase a cluster, and the latest technology will be purchased in that exercise. And then at some point in the future, when there needs to be more capacity, there's typically a new acquisition cycle for what is the latest technology at that point in time, right? And then you get a separate cluster, okay? So that's typically how these things work. Also, if you're dealing with the governments or with higher ed, they typically have what we call opportunity funding, where they have an envelope of capital funds available, and they go out and they'll make a capital purchase. And this is kind of how we see these things presented to vendors. They'll say, look, I have X number of dollars available to me, and how much stuff can you give me for my money? And that's how they do their evaluation, right? So, vendor A, like if the funding envelope is $500,000, vendor A will say, look, I can give you 4,800 cores. And vendor B says, I can give you 5,200 cores. And it's like, well, you got more cores, you get the business. So that's a typical acquisition approach. Also, it's not unusual to find benchmarking as a requirement during the tendering process. So they will, the customer will ask for a benchmark to be run and to be submitted with the bid. Because clusters are assembled from a bunch of components, okay, and assembled into a single unit, customers will typically ask for total solution support from the supplier because it's being assembled from components that come from multiple vendors. The purchaser typically wants to offload the risk of managing those multiple vendors and push that back onto the supplier. So it's not unusual for people in this business to have consolidated warranty service for the combination of equipment. I go back earlier to the customer as a choice of purchasing, white box machines or from a tier one. This is one of the reasons why the tier one vendors tend to dominate this market, because if you assemble it yourself, if you roll your own, as they say, the customer himself takes the burden on them to support the combination of equipment, which is not always palatable. In fact, even in higher ed, where there's more appetite for supporting equipment and supporting applications in-house, even higher ed customers are predisposed to purchasing it from tier one vendors. And then the final thing here is, as I mentioned, it's typically opportunity funding. They're typically purchased with 3 or 5. I know in my business, we sell these things with a 7-year warranty. And then when the clock runs out on the warranty or when new opportunity funding appears, then an entire new cluster is stood up. And then customers live with sort of like there's, generation 1 cluster that I'm going to use for a certain number of apps, and I have generation 2, which I'm going to use for something else. And we sort of separate our application requirements by cluster. So that's a typical way to do it, as opposed to having like a single big cluster that I expand, because that's not really the case. People don't do that. That's the end of my presentation. Hopefully that was informative. If there are questions, please feel free to reach out and contact me. Thank you.